Okay, hello. We're back to logic. This is second, well, I guess third technically lecture in the class. Okay, let me share the screen with you and come back to where I believe we were last time. So, so we introduced predicates, quantifiers, quantified statements, and we had the quantifier there is an x such that some predicate on it holds, and a predicate for all. Okay, and we have seen some examples of how to evaluate them, right? So, okay, and then we said that there exists an existential quantifier. There exists x such that tx. When you have a finite domain, this is equivalent to a big disjunction, because what you're saying is that there exists an argument on which predicate t holds, and if you know that the domain contains 27 arguments, then this is the same as to saying that predicate t either holds on the first argument, or on the second, or on the third, and so forth, right? And conversely, universal quantifier on a finite domain, to say that for all x's in that domain, t predicate t holds on x. By the way, this is the terminology. If instead of saying t of x, I can say predicate t holds on argument x, and that's the same thing. So instead of saying that for all x, predicate t holds for that x, I can say, in the case of a finite domain, that predicate t holds on the first element of x domain, on the domain, and it holds on the second argument, and it holds on the second and the third, and so forth, right? But this kind of statement makes sense only if the domain is closed, is finite, right? Or otherwise, this would be an infinite sequence of symbols. Okay, let's look at some examples of how to assign truth values to predicates to statements which have universal or existential quantifiers. So here is this, let p of x be a predicate that x is prime. Okay, so the natural domain is positive integers. Okay, and what does it mean as a prime? It doesn't have non-trivial divisors. So for example, 6 is not a prime because it's divided by 2 and 3. But 3 is a prime. 4 is not prime, it's divided by 2. 5 is a prime. 7 is a prime. 11 is a prime. Okay. And d of x is just a predicate that x is odd. Okay, so let's see this statement. For all x's, if x is prime, then x is odd. That's what this statement says. It is true if it is the case that for all x's in the domain of positive integers, it does hold that if x is prime, so the hypothesis in this implication is made true, then the consequence must also occur, right? So the minute that some integer is prime, we can conclude that it's also odd. Okay, so most primes are odd, right? Because if they are even, then they are divisible by 2. So therefore, that's a non-trivial factor, right? So 4 is not prime. It's divisible by 2, 6, 8, all even. Okay, except 2 itself. 2 does not have non-trivial divisors. It is actually a prime, and 2 is not odd. So the statement that for all x's in the domain, this implication holds is not true. There exists an x which makes this statement false, and that's the x that makes this part true and this part false. And that the only x like that is 2. Okay, it is prime indeed, doesn't have non-trivial divisors. but this is not odd. Okay, now let's say a modified formula. For all x's, it holds that if x is prime, then either x is odd or x is equal to 2. And now that implication is true, because the only way to falsify this one was to take this one counterexample. The same counterexample now does not work, because it actually makes the consequence true. Simply this part is true, trivially, about x equal 2. Okay, so what does this say again? For all integers, if an integer is prime, then it must be the case that either this integer is odd or the integer is 2. In other words, every prime has one of the two properties. Is either 2 or it's odd. In other words, every non-odd, every prime greater than 2 is odd. Okay, now that is true. Okay. We could have expressed this differently. We could have said for every x, if p of x and x not equal to 2, then odd x. Okay, and it's an exercise whether these two statements, this statement is equivalent to the one I just said. Let's look at another example. For all x, here is an implication. If x is negative, then it is a prime. But first of all, negative numbers are not considered primes. Okay, a prime is a positive integer that has non-trivial factors. So all negative integers would not be. But in any event, we don't even have to worry about this because our domain is positive integers. So this quantification is supposed to quantify x universally over the domain of positive integers. So the fact that there are negative, okay, so what about this part? Okay, well, this is not so hard actually, because this part is simply never true. For all x's in the domain, x less than 0 is false. So this implication is equivalent to an implication that says something false implies x is prime. Okay, consider two cases, x prime and x not prime. Since this holds for all x's, this will exhaust the cases, right? Because every integer is either prime or not. You see, for one of these cases, this is false and this is true, and for the other, this is false and this is false. That doesn't actually change how the value of the implication, because an implication from false to whatever, it can be true, it can be false, is true. If you check out the truth table of an implication, the moment hypothesis is false, implication is true, right? So an example I didn't give last time that I really like is from the Fiddler on the Roof. There is a song, if I were a rich man, da, 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 you know, I could do this and I could do that and I would do this if I were a rich man. The thing is, the person who sings this is not a rich man. And therefore, anything that he sings as a consequence of being rich is by definition not so important. It does not really matter whether he promises that he will do this or that, or brings the stars to his daughter, or whatever else to other people he loves. He's not a rich man. So these implications that he sings are true. They can never be proven otherwise, because sadly he is not rich. Okay. It's the same with these integers here. They're never negative. So therefore, under that promise, whether we conclude that they're prime or not, it does not matter. The promise is never realized over that domain. There are some rules for about reasoning on quantified statements. The book lists a longer list of laws that, again, as in the standard logic without quantifiers, right? Like, it's good to go through and understand, but you don't have to remember them and you have to remember their names. Just make sure that you understand why this is true. So here is the Demorgan law for quantified statements. To say that it is not true that there exists an X for which Px holds is the same as to say that for all X's in the domain, P of X is false. These are equivalent statements because the left-hand side says it's not true that Px holds on right, that there exists an X. So there exists an X for which Px holds. In other words, Px never holds. There is no X that makes Px true. So Px is always false. The right-hand side is says the same thing, but just in a different way. It says that for all X's, X is false. Sorry, P of X is false. Okay, in other words, for all X, Px is false. So Px always false. It's the same. Here is one way that you can see it. If you assume finite domain, or in fact, in a more general way, any enumerable domain, then to say that the existential quantifier is there exists xpx is false, it's the same to say that the following thing is false. It's P holds either on V1 or on V2 or all elements in the domain. And now use the standard Demorgan law. A negation of a big disjunction is the same as conjunction of negated components, right? To say that it's not true that either this or that or this or this or this is the same as to say not this and not that and so forth, right? And now combine them and you'll see that this is actually an instance of this is the right hand side. Okay, so so you have a proof of the Demorgan law on universal quantifiers for enumerable domains, domains where you can list elements, which is in any event everything that you care about in this class. The converse also is true. So to say that it's not true that for all X, Px holds is the same as to say, so we have a connection issue. Okay, let me hold on. Let me get. Sorry, I have a cable in the other room. Sorry about that. Okay. Let me check. Hold on a second. Let me. Okay. Well, I will hope that it's better now. I cannot really test it. Okay. So I'm going under the assumption that the connection is better. Okay. Thanks. Somebody just confirmed this. All right. Thank you. Great. So, okay. So both say the same thing because me get a better pointer here. Yeah. This one says it's not true that P holds for all x's. Okay, it's not true that predicate P holds everywhere. In other words, there is some counterexample. There exists an x for which this predicate does not hold. Okay, and vice versa, right? It's the same statement. And you can likewise see that this part is really, when you envelop it, it's a negation of one big conjunction, that this predicate holds for first, for second, for third, etc. And if you negate this, this means that it must be not hold for either for the first or for the second or etc., which is expressed here. Okay, some simple laws for quantified statements. So this is like the simplest law. Okay, I mean, okay, the Demorgan is one of them, but perhaps not so simple. This one it really is. It just says, look, if you're saying that predicate P holds for all elements in the domain, then in particular you're saying that it holds for some. Okay, this is a non-controversial statement, right? Now let's look at the negation. If you are saying that it's not true that there exists an x which makes the predicate hold, for which predicate holds, so that implies that it's also not true that the predicate holds for all x's. Okay, again, should be not controversial. If it's not true that there even exists some x that makes the true, then it's also not true that all x's make px true, right? And actually, you can see this is true as by putting this in a counterpositive, because this is an implication of the form P implies Q. And if you put it in a counterpositive form, which is equivalent, then that says that not Q implies not P. In other words, and this is exactly not this part. Well, this is exactly not this part. Okay, so you can see that statement 2 follows from statement 1 by a counterpositive. You can also use Demorgan laws, right? So because if it's not true that there exists x, then that's the same as to say that for all x's, negation holds. And now I just switch it here by thinking of this as P prime, where P prime stands for not Px. And if I do that, right, then the fact that for all x's P prime holds implies there exists an x for which P prime holds, implies that if for all x's not PQ, not P of x, then there exists an x such that not P of x. And by Demorgan, this in turn is equivalent to that, which is this side. Okay, so it just shows that you can use different reasoning to arrive at the same thing. So now we just showed that statement 1 implies statement 2 in one way here and in a different way here. Let's look at some example of quantified statements. So, of course, in the textbook and in the homework, you have many examples to test you. Try to say, okay, how do I evaluate such a quantified expression? Is this quantified expression true or is it false? How to exhibit this quickly? How to point out, is it a counterexample that proves that the quantified expression is holds or that it doesn't hold? Yes, let's look at some commonly occurring ones. So, for example, here is a natural statement. There exists an x which makes both predicate P and predicate Q true. Okay. Or for example, I want to state that for every x in the domain, if some predicate holds on it, P, then also a predicate Q must hold on it. In other words, Q holds whenever P does. Okay, let's think, like, let's say if the P predicate says that something is divisible by 4, an integer is divisible, is a multiple of 4, and Q says that an integer is a multiple of 2. Well, then for all x, if x is a multiple of 4, then x is also a multiple of 2. Okay, not the other way. For example, 6 is a multiple of 2, but it's not a multiple of 4, right? So the two predicates are not equivalent, but one implies the other on all elements in the domain. This implication can be put in a different form, namely this one. This way of using a universal quantifier really stands for this implication. And let me read this for you. This thing says, for all x's which are restricted, namely x such that P of x holds on it. For all such x's, Q of x must hold. This form of universal quantifier is a universal quantifier with a restriction. So you can think of this, that the domain on which this x goes is not the original domain, but a partition, part of it, for which this predicate holds. And I'm only in this statement saying anything about x's which belong to this restricted subdomain, if you will. And I'm saying Q holds for all of them. This is exactly stated here. For all x's in the top level domain, right, the unrestricted one, if they belong to the subdomain, those which are for which P holds, then Q holds for them. That's exactly what this says. This is just a different form. It's often used. Okay, and this statement can be like, if you don't know how to think of this, you can think of this as a case of this. Here is some a natural question. What would be if you say there exists an x such that something holds, for which Q holds? That's actually this. So there exists an x, if I write here such that P of x and only have Q of x as a as my statement about those x's, this is equivalent to saying this. Okay. Here's an example of an unusual, tricky statement, which don't occur in like a normal person should not say stuff like that in usual circumstances, except to test your understanding of predicate statements and how to evaluate truth or falsity of a predicate statement. In other words, on homework and as an examples in the book and on the test. So there exists an x such that P of x implies Q of x. This statement says, if you think of implication and remember this law, that an implication A implies B is the same as to say that either not A or B. Okay, remember that? So this statement that there exists an x for which Px implies Qx is equivalent to saying that there exists an x for which either the predicate P fails or predicate Q holds. Now, this is a natural statement. You can indeed say there exists an x that satisfies, I mean, you can say everything. right? I'm just saying which of these statements are natural, commonly occur, and actually, are not just designed to trick you, but they are commonly occurring, that in reasoning. So this statement is a natural one. It says there exists an X for which one of the two conditions hold. Either X falsifies predicate P, or X is true, or Q holds for X. Okay. If you think that this is expressing some sort of admission criteria for something, or like expressing when you should treat someone, okay, based on some predicate about their previous history and medical condition. So you can have a predicate that says, I'm going to administer the treatment if either something is true but some other thing is false. Like, for example, temperature of the patient less than something, right? The point is that the second one is clear to read, and the first one is equivalent. And if you remember what an implication is, and that the implication is equivalent to this statement, then for you there is no difference between this and that. However, this kind of tests your fastness in logic, because this is a statement that is bound to confuse people who don't have logic at the tip of their fingers or whatever the expression is, and they might read this sort of in a similar way as this one. Okay. 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 So the homework and the textbook have many examples of these type of statements, and like, hey, this can be actually trivially true, just because it becomes true. So, for example, let's say that you say there exists an X such that some crazy thing about X implies some reasonable thing. Well, this is actually true. There exists an X such like this, right? Because a crazy thing is never true, so it's easy to find an X for which the crazy thing is false, and therefore the implication will be true. It's obvious when you read it in this form, but okay, maybe takes a little bit when you see it in this form. Now we can nest quantifiers. So it makes perfect sense to say something like, for all x's, there exists a y such that some formula involving both x and y holds. Okay. The way to think about these nested quantifiers is to kind of, in your mind, unnest them. Okay, and I'm giving you some sort of slow guideline for what that stands for. So imagine that you have a predicate that involves two variables, x and y. For example, t, which I will read as twice xy, okay, which is a predicate that says it holds if 2x make a y. In other words, twice 1, 2 is true. 2 is twice of 1, but twice 1, 3 is false. 3 is not twice of 1. Okay, now consider a predicate that says p of y is true if there exists an x such that twice xy is true. Let's evaluate. Is p of 2 true? And I say yes, because there exists an x which makes tx, 2 true. Because what is t of x2? That 2x equals y, which is 2 here. So this stands for 2x equals 2. There exists an x such that 2x equal 2, x equal 1. The implicit domain here is positive integers. Okay? But p of 3 is false. because there exists no x such that t of x3 is true. Namely, for all x, this predicate is falsified, right? Because there is no x, integer x, such that twice x equals to 3. It's not only that t of 1, 3 is false. In fact, t of any x, comma 3 is false. In other words, p of 3 is false. Okay? And now let's go up one layer. And since p is a predicate on y's, and we have just seen that it's true for one integer, namely 2, and it's false for some other integer, namely 3, so it makes sense to say stuff like, there exists a y for which p of y is true. Or perhaps for all y, p of y is true, right? P of y holds. This predicate is true. This quantified expression is true. Sorry, not predicate. Quantified expression is true. We have just seen an example because it is made true for y equal 2. There's other examples. It's also made true if y equals 4, right? This statement, if you put this statement for y equals 4, is also true. There exists an x such that t of x 4, namely x equal 2. It actually is true for all even integers, right? So any even integer is a proof that this statement is true. But this statement is not true. It's falsified by y equals 3, as we have just go over, right? P of 3 is false, so therefore this is false. Any odd integer is a proof that this statement is false, right? Because take any odd y, p of that y does not hold. Yes, because there is no x that multiplied by 2 gives you an odd integer. And if you stick this formula, if you replace p of y with the fully with this definition, then this statement gets when you envelop it, you have this statement in it. I mean, this statement is equivalent to this one, right? What you're saying here is that there exists a y such that py holds, but what is py? It's this statement. In other words, there exists a y such that this thing, there exists an x such that t of xy. And if you read off the previous examples, one example that is true, that makes it true, is this one. The universal formula for all y, p of y, if you envelop it, it's a series of quantifiers that goes for all y, there exists an x such that t of xy. And again, this is false. It's the same counterexample that we've seen, right? Because all I'm doing here is just reading off what the statements with truth or false I already argued, how to read off the statement with full quantifiers and predicate t. Going backwards, if you see an example like this, okay, you have some predicate like this one, and you're supposed to evaluate what is the truthfulness of the following statement. For all y, there exists an x such that this predicate holds. If you are not sure, basically what that predicate stands for is go from so you have, this is a fully quantified expression. Both x and y are quantified in it. Okay, so therefore there is some truth value to it. It's either true or false, but it's well defined. Take the predicate and just move one just take the quantifier immediately before it and put a bracket here. Think of the inside as a predicate about what variable? Well, the unquantified one, namely y. So from here on, this statement is a predicate about y. For some y's, it is true. For some y's, it is false. But first, think of this inside as a predicate on y. And then once you understand what that goes and for what y's it's true, for what y's it's false, then you can evaluate the full expression. Because once you understood whether this inside thing as a predicate on y, is it always true for all y? Is it sometimes true? It's like never true, perhaps? Then you can answer this question, right? Okay, because this series of quantifiers, they really can be rewritten as a normal quantified expression over a modified predicate. In this case, the modified predicate involves a level of quantification at one more variable, x. Let's look at some examples. So let's say the predicate is x is smaller than y. Okay, that's like this txy predicate on the previous slide. And let the domain, these things are very sensitive to the exact specification of domain. The domain is, in this case, positive integers. So from 1 on. Is this true when I say that there exists an x such that for all y, x is smaller than y in this domain? Both x and y are bound by the quantifiers. So this is a statement that is fully quantified, and therefore it's either true or false. It is false. Why? I'm claiming that for all x's, there exists. Hold on a second. There exists an x such that for all y. So in order to show that this is false, I have to show that for all x's, the opposite holds. Namely, that there exists some y that is that makes this statement true, false. That y is not greater than x. Maybe some of you can guess what that y is. Okay, so somebody says, let's take x1 and make y1. Yes, this makes this false, but it makes it false for a particular x. I want you to make this part, show that this part is false for all x. Doesn't matter what x is. Good. Somebody said y equal x. So this statement says that for all x's, something is true about x. What is this thing? Is that that all y's are greater than x. All elements in the domain are greater than x. That there exists an x such that all elements in the domain are greater than it. Let's see that this is never true. In fact, that for all x's, this predicate is false. Namely, there always exists some y, which makes this false. What is this y? Well, perhaps it's x minus 1. Yes, then if y is x minus 1, then this clearly falsifies. But that's almost a good example. Why almost? It works for every x that is at least 2. Because, yes, for 2, there exists an x minus 1 is 1. For 3, there exists x minus 1 is 2. at software. And if y is x minus 1, this will work great as a counterexample, except for x equal 1. So for x equal 1, you need a new counterexample. It's not y is not going to be something smaller than x, but it's enough if y is equal to x. Y that is equal to x makes this statement false. So therefore, for every x, there exists a y which makes this false. A good example that works for all x's is y equals to x. Okay. How about this one? For all y's, there exists an x which is smaller than y. Both x and y are bound by these quantifiers, so it's well defined. It's either true or false. So let's see, I'm saying it is false. In order to show that it's false, I have to show that there exists some y. I have to show you one y for which the following thing is, for which the following holds. For all x's, sorry, there exists one y that this is false. In other words, there is no x that is smaller than y. Give me an example of this y. What is this? There is only one counterexample to this. Only one value of y, which makes this part false. This predicate on y, this is a predicate on y. The predicate on y says that there is something smaller than y. That's what this thing says. This is the predicate on y. It says there is something smaller than y. This predicate is true about 3. There is stuff that is smaller than 3. So 3 is not a good counterexample because there is stuff that is smaller, 1 or 2. What is this one y for which is going to make this false? Come on. Yeah, y equal 1. Yes, right. So y equal 1, there is no x that is smaller than 1. Yes, this predicate is false for y equal 1, and that's the only one. For all otherwise, this is true. There exists an element smaller, right? Statement like there exists an x such that x is smaller than y cannot be evaluated because we don't know what the y is. It's true for some, yes, for y equal 3, this is true. For y equal 1, it is not true. Or this one, that for all y, x is smaller than y. We don't know what x is. It has to be bound by some quantifier. Are you saying this for all x, or there exists an x? We don't know. Okay, I messed up the animation here, but just ignore this part for the time being. So let's go with this twice t of xy example. And oh my goodness. Okay, and let's say that I have these quantifiers, these expressions. There exists an y such that there exists an x, that t of xy. Or for all y, there exists an x such that t of xy. Okay, I know how to handle it, right? Because I'm just going to define a predicate that expresses this part. And it's a predicate on y. That's what I did here. And yeah, so this predicate on y says that y can be expressed by twice some other integer. That's what this thing says. So now, so now I have an understanding of what is the meaning of the inner predicate on y. It simply says that y is twice some other integer. In other words, y is even. That's what this thing says. So these statements can be rewritten as the first one, there exists an y which is even, and the second, for all y's are even. Okay, then it's obvious how to evaluate them, right? The first one is true because there exists the domain is integers. There exist even integers, and it's not true that all integers are even. Okay, let's say that that the inner part was that you had this type of quantified expression. There exists y such that for all x's, g of xy. Now what? Okay, but use the same logic. Identify the inner part as some predicate on y. What is that predicate? The predicate says that for all x's, g of xy. What is this? Let's call it q of y. The predicate says for all x's, g of xy. In other words, for all x's, y is twice x. Now, that's a crazy predicate, right? There is no integers such that this predicate is false for all integers y. Because for q to be true about some y, it has to be that y is twice all other integers. Okay, and you know that that cannot be true about any integers, that's twice all others, right? So it's a false predicate. Okay, so whether you say that there exists a y for which it is holds, or that for all y's it holds, it's false either way. Okay, so now let's switch these, and instead of saying for all there exists a y, or okay, let's switch the order and see how the order influences, or does it at all, the truth or false of this. So is this statement the same as this one? Is this statement the same as maybe this one? Because it's for all x here and for all x, and there exists and there exists. Let's test that. So let's use our method, right? Which is, let's identify this inner thing as a predicate on x now. Yes, because in the inner thing, x is outside of quantification. So it's not a statement, but it's a predicate on x. So the green predicate, this part is going to be written using the green predicate s of x. What is this predicate? It says there exists a y such that g of xy. In other words, that that there exists a y such that 2x equals y. Well, this is a trivial predicate. It's that x is half of some other integer, that 2x is another integer. Well, you know that is true. If you start from an integer, there always is an integer that is twice bigger. So that's true for all x. So if you can rewrite these as there exists an x for which this inner expression is true, or there all x such that this inner expression is true. And both of these are true because s of x is a kind of trivially always true predicate. Okay, just by laws of arithmetics, right? You know that for every integer x, 2 of x always exists, and it's some other integer, or also an integer. But let's look at these cases. Now inside of the bracket is that for all y t of xy. What is this? For all y t of xy is that 2x, for all y, it is the case that 2x equals to y. Now that's sort of a nonsensical predicate. It's always false. It's not true that for no x is it true that x is half of all integers. It is x is a half of some integer. The integer is twice x, but it's not half of all integers. So these statements are, this predicate is false for all x, and therefore, whether you quantify it for the existent x, for which is true, or for all x is true, it's false. Now, this statement and this statement are always the same, no matter what t is. They happen to have the same truth values here. I mean, okay, so the fact that they have the same truth values here is not a coincidence. In fact, I didn't have to evaluate this once I knew the truth value of this. In other words, if you have a predicate and quantifiers that say there is some x, such that there is some y, such that perhaps there is some z, such that some statement in only x, y, z holds. It doesn't matter how you order x, y, z. Okay, because all of these, both this and this, say that there is some way to instantiate variables y and x and y thing, such that this predicate holds for that particular instance of x and that particular instance of y, and therefore it doesn't matter in which order you instantiate them. If there is a satisfying assignment, then you can instantiate them, you can assign x and y and z and whatever to these values in whatever order you want. There either is a satisfying assignment or there isn't. Okay, so these two statements have always the same truth value. Likewise, these ones, because they say that this predicate holds, does not matter how you instantiate x and y. For every instantiation of y, for every instantiation of x, again, the order doesn't matter. However, the order in which basically when you have different quantifiers here, then you cannot switch them. So there's two ways of switching. One way is to, okay, instead of, here I say for all y, there exists an x. So how about for all x, there exists a y? And it's completely different statement. And here you have an example where one is false and one is true. Okay, this statement involved the inner predicate of it was the existence of such numbers which whether it's true that every integer is twice of something. This thing says, is it true that every integer can be multiplied by 2? That's a very different statement. Another way of switching quantifiers would be just to replace their order. So in that case, a natural way of switching for every y there exists an x would perhaps be this thing, that for every x, that there exists an x for which there's all, just switching the order. Now, if I switch the order here, so this statement is the same as the blue, but with switched order. Well, that happens to be false as well. So perhaps your hypothesis is like, well, okay, maybe I can always do that. This statement and the green statement is examples that you cannot. So this statement has the same quantifiers here, but as the green statement, this one. This one has the same as the green, just in a different order. And this one is false, but the green one is true. Okay, so in general, switching either the order of the quantifiers, if they're different. So the only way you can switch order if they are the same, if this is the same quantifier, so both existential or both universal. But if they're different quantifiers, then switching the order might swap from a false statement to a true. So yes, replacing. Okay, as I said before. Okay. Yeah. So I believe this person must have asked before I was talking about it. So yeah, yeah. I hope I just answered the questions that were on the chat. Okay, many more examples in the book and in the homework. So let's move to the new topic, the sets. Okay, so we will not get to functions today. It's okay. We use curly brackets to express sets. This is the sort of the standard notation for sets which are of finite size. Just put the curly bracket and list all the elements. Set is an object where if you list all the elements, it does not matter in what order you list them. So if you define a set as either in this way or in that way, it doesn't matter, it's still the same set. These items are called elements of a set. So for example, if S is a set like defined like this, it's a set of 4 elements. First, there is an A is an element, B is an element, C is an element, D is an element. It doesn't make sense to say first or second element. There is no such thing because order does not matter. And here is a special symbol that lets us express that something is an element of some set. And this is this expression is read: B is a member of set S, or B is an element in set S. If you want to say that something is not an element of a set, you have a special notation for that too. Just the set membership notation crossed out. Okay, so this is read: E is not an element of S. So you can have infinite sets with infinite number of elements, like for example, the set of all integers, right? It's not a finite set. And for example, set of ICS.6D students is a finite set. If S is a finite set, then we can then its cardinality is well defined, and the cardinality of a set is simply the number of elements in the set. So this set had 4 elements. Its cardinality is 4. Cardinality is designated by vertical bars before and after the set. So if S is a set, then bar S bar stands for cardinality of set S. Here is some famous sets for which you should learn what these letters stand for. So natural numbers is designated N with like a thickened bar, and I will always try to remind you of this and not trick you to make you remember. But that said, you should remember that natural numbers are non-negative integers, so they start from 0. There is different conventions, and like in different centuries, people use the same natural numbers to only be numbers from 1 on. Okay, so there is, in a sense, good reasons to not remember, but we will use the convention and that natural number starts from 0. And I think everybody uses that nowadays. The integers, the symbol is Z, again with a thickened diagonal, is all integers. So not just naturals, but also negative. Q is a set of rational numbers. So any number that can be expressed as a division of 2 integers with the denominator non-zero. R is the real numbers. And there are some other sets like imaginary numbers, complex numbers, right? And you can have other algebraic objects. We will actually come back to it in modular arithmetics. But here is another famous notation for a special notation for an empty set. Is crossed out 0, but we will most commonly use this notation for an empty set. So just open closed bar means a set with nothing in it. So we would the common also sets are formed as subsets of those. For example, when I say Z plus, I mean all the elements of Z which are positive, okay, meaning they're greater than 0. Z plus is not the same as natural. There's one difference, right? 0 is not in Z plus, but it is in natural. Right, so Z plus is natural plus, natural is Z plus 0. You can say also R plus or Q plus, right? That's the reals, but only positive ones, rationals only positive. And likewise, the minus sign. When you say that a number is positive, right, it means greater than 0, negative less, and non-negative is slightly different from positive, right? Almost the same, except 0 is not positive, but it is non-negative. The listing elements in using curly bracket notation is called the roster notation. Okay, so using the roster notation, I can list the elements of some set of 4 elements, 1, 3, 5, 9. You can use the ... as a kind of an inferred pattern. So rather than write a set of odd integers between 1 and 99 using 50 or 49, I don't remember, right, characters, it's enough to just say 1, 3, 5, ... because somebody will understand that's the pattern you mean. Or I can define a set of infinite set of all odd integers this way. Of course, it relies on you understanding on the reader to understand the pattern, the same one that the person who wrote it had, right? So it's an implicit pattern that nevertheless is sort of easy to infer. For example, here is the case, there is a pattern, right? But it might not be so easy to infer, right? So, and in particular, I was thinking of, any integer that looks like a square minus 1. Okay, so yeah, like 4 minus 1, 9, and 16 minus 1, etc. But that pattern might not be obvious. Okay, so in order to build sets using, in a more general way, we use so-called set builder notation. It's the set builder notation is like this: curly brackets as before, but instead of listing all elements explicitly, you say X such that X is in satisfies some condition. So, so for example, here is a set builder notation using this. This is a set of all integers n, of all elements n, such that n divided by 2 is a positive integer. What set did I define? All even positive integers. So this set includes all n's which are positive and even. Okay, because these are the only n's such that if I divide them by 2, I get a positive integer. Okay. I could I could equivalently define them using this type of notation, where instead of saying some x such that, and here's a condition on x, I say some function of x such that x. So for example, here, this is a set builder that says the elements of it are of the form 2n, such that n satisfying the following condition. N divided by 3 is the positive integer. So what are the n's that satisfy this condition? N equal to 3, n equal to 6, n equal to 9, all n's which are divisible by 3. But my set does not define as simply containing such n's. No, it contains elements of the form 2 times those. So if those elements were 3, 9, 3, 6, 9, etc., then my set contains twice that, 6, 12, 18, okay? So this set builder, this set in a better way would be described like this. It's a set of all elements of the form n squared minus 1, such that n is an integer, okay? Except that I wouldn't get a 0 this way, so I would better say here natural, right? So if I say z plus, then no, yeah, actually it is, right? Because the first positive integer is a 1, 1 squared minus 1 is a 0. The second is 2, 2 squared is 4 minus 1 is 3. Okay, yeah. So by manipulating this expression and manipulating the constraints, you can define all sorts of complicated sets. Okay, this could be a Boolean expression involving, right? This is a simple expression. It says half of n is in this set, but it could be a conjunction, like either half of n is in this set or a third of n is in some other set, right? Here is the notion of what a subset means. We express the fact that T is a subset of S using this symbol. T is and we read it, subset of S. Pictorially, the fact that T is a subset of S means that if I drew all elements of set S, then T must be contained inside of S somehow. Okay, every element of T is also an element of S. And this is the definition of a subset. T is a subset of S if the following predicate holds. It's a quantified expression, sorry, not predicate. If the following proposition holds. This proposition is a quantified Boolean formula. It says, for all x's, the following implication is true. The implication is that if x is a member of T, then x must be also the member of S. Okay, this logical formula is the same as to say T is a subset of S. And you can see this sort of pictorially. Indeed, if this white space includes all elements of the domain, then for any element in the domain, it is true, no matter how instantiated, that if this predicate holds, then this one also does. If x is outside of set T, in other words, this predicate is false, then the implication trivially is true, right? Because, okay, that's what we said about implication. We say this every time, that implication is true, that if the hypothesis is false, then the implication is true. So everywhere outside, if x is anything outside of T, this holds. Okay, good. So we checked that this holds for everybody outside of T. What about the inside of T? So this part is true, and therefore this must be also where it is true when T is a subset of S, right? For all elements here, they're also elements of S. To show that something is not a subset, you have to show one counterexample. In other words, some element X which belongs to T but does not belong to S. So let's take some examples, like S is a set of ABC, T is ABC, so it is a subset. But V is not a subset of S, right? Because E is some element that sticks out. And likewise, V is also not a subset of T. In fact, this statement follows from these two. Okay. In a sense, a subset relationship can be interpreted exactly as a statement that an implication holds between two predicates. Okay, so if the sets, using a set builder notation, they naturally correspond to some predicate. Namely, I can define a set X as all elements for which some predicate holds. So a logical predicate corresponds to a set of all elements which makes the predicate true. If you think this way of sets, that they are basically a predicate, okay, and conversely, you can, for any set, you can define a predicate. What's the predicate associated with a set? It's a predicate that this element is in the set. It is true about all elements in the set, and it's false about all elements outside. But it's a predicate naturally defined by a set. So set and predicates go hand in hand. And to say that set T is an element of set S is the same as to say that the predicate that defines set T implies the predicate defined, the predicate that is defined by set T implies the predicate defined by set S. Okay. Let's look at set union. Okay, so what about other Boolean formulas involving predicates? Do they correspond to some operations on sets? Yes. So here's a union of sets. Union of sets denoted by union of set A and set B is denoted with this letter that looks like a U. Okay, so stands for union. And how is the union defined? Well, it's defined by a following predicate. Every element belongs, and an element belongs to a union of the sets if either it belongs to the first or to the second, or of course to both, right? Because this junction is always an inclusive one. So pictorially, if you take a union of two sets, it's like this black set, which is all the area that is either blue or red, or the intersection is part of the union. A union corresponds to a disjunction between two predicates. This black set is defined if A is associated with some predicate, call it PA. It's a predicate that defines set A. Namely, elements of set A are X's which satisfy predicate PA. Set B is defined in terms of predicate PB. Then their union is defined in terms of the predicate either PA or PB, right? And the union of two sets corresponds to a predicate which is a disjunction of the predicate defining set A and the predicate defining set B. What about conjunction? What set is defined by a conjunction of a predicate PA and a predicate PB? In other words, it's a set of all elements which satisfy both the predicate PA and the predicate PB. Well, it's this area. It's the elements that belong to both A and to B. That's called set intersection, and it's denoted with the inverse sign of union, okay? This time. And pictorially, this is now intersection is this area, right? Those are the only elements that satisfy both that they belong to A and that they belong to B. Set difference, I denoted with a slash. The textbook denoted with a minus sign. These are alternative notations. People use either one. You should know both. Okay. Set difference can be denoted with the same difference as you know, in integer difference between two integers, right? But there is a special notation that sort of signifies, oh, this is a difference of sets, and it's with this slash sign. A set difference corresponds to the following predicate. And elements of a difference between A and B are x's such that they belong to A and they do not belong to B. In other words, the set difference between A and set B is this area. It is an asymmetric operation. The union of A and B is the same as the union of B and A. Intersection of A and B is the same as the intersection of B and A. Set difference is different. A minus B is not the same as B minus A, right? So B minus A would be this red fragment with this part out, right? And negation in Boolean logic also has a natural equivalent in set algebra. It's a complement. So when I want to define a set, so if A is a set defined by some predicate associated with it, and as I said, every set has a natural predicate satisfied by elements of set A and nothing else. And for every predicate, there is a set, right? So what set is built by negating the predicate that builds set A? The set that is a complement of set A. This set is a complement of A. It includes all x's that do not belong to A. So x belongs to a complement, even on if it is not true that x belongs to A. In other words, that x does not belong to A. In order to define what a complement is, we have to have a notion of what the universe is, what is total domain, right? You know, if we look at, you know, all students, the complement of ICS.6D students is, you know, is not made of every object in the universe, which happens not to be a ICS.6D student, right? It's more natural to say, okay, in the universe of UCI students, a complement of ICS.6D students would be those students that do not take ICS quarter, right? So here the implicit universe is going to play a role. Okay, so this I give you an examples. Okay, look at these examples on your own, and we'll start from here next time. Let me stop recording.